Hey guys, welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So people, quickly let me know in the chats if all of you can hear me, if I'm perfectly audible and visible to everyone. Quickly let me know in the chats with the thumbs ups. Everyone guys, everyone. Let me know quickly in the chats, people, if all of you can hear me, if I'm perfectly audible, visible. Yes? All good? All good? So, are you guys ready to rock the session? Perfect, guys. Wonderful. The Josh is high, it seems, yeah? So, first of all, if you have just joined the channel, if you have not liked the session yet, I would want you guys to like the session. Share this particular session with everyone. Whosoever is preparing for NEET 2023, this particular session is for every single one, right? Let everyone get benefited out of these sessions. And at the same time, majority of the students have been asking me about the top 50 concepts, right? So my dear students, we are doing the top 50 concepts only basically. It is just we have rebranded this series and now the name of the series is Final Lap. Rest everything is same, you do not have to worry at all. Everything in detail will be discussed here. Okay? So are you guys ready with your pen and paper? Should we start? Give me some green signal from the chats. Let me know quickly in the chats. Let me know quickly in the chats. And one more thing I would want you guys to know, this session might take more than 2 hours, right? So I would want you guys to be with me till the end. So for sure, the kind of concepts which I'm going to give you in the today's session, trust me, you guys are going to get almost 4 to 5 questions from the same concepts in your NEET 2023 examination. For sure. You can mark my words as well. Yeah? All right then. Perfect. So are you guys ready to be with me till the end? Yes? Are you guys ready to be with me till the end? The Josh in the chats, I want to see exactly. Are you guys ready to be with me till the end? Perfect, guys. Wonderful. So people are saying if it is 3 hours also, we are ready. That's wonderful. That's great. I like the spirit. All right, people. So let's focus on the session now. Rest of the things I'll be talking, whatever doubts you'll be having, right? I'll be dealing with your doubts at the end of the session, okay? Let's not waste a lot of our time. Perfect. Perfect. Wonderful. So people, our first concept of the tonight's session is going to be empirical and molecular formula. Empirical and molecular formula. One of the important topics from which question have been frequently asked in your NEET examination. Okay, you can expect one short question on this concept as well in this upcoming NEET examination. So let's have a look what this concept is all about. See guys, for example, I'm writing glucose. I'm writing glucose over here. Right? If I ask you, what is the formula of the glucose? You will simply say the formula of the glucose is, which you have been studying till now, it's C6H12O6, right? It's C6H12O6. Every one of you will come up with this, correct? Yeah. The formula of the glucose, you will say it's C6H12O6. If you look at this particular formula, if I ask you, in glucose, how many different elements are there? There are 3 different elements in glucose. As you can see over here, carbon, hydrogen and oxygen. Now, if I ask you, what is the ratio of the atoms of different elements in glucose? You will say the ratio of the atoms of different elements in glucose, it is 6:12:6. This is something which you guys are going to tell me, correct? So basically, I took glucose, I wrote its formula. Now, I wrote the ratio of the atoms. I wrote the ratio of the atoms of different elements in case of glucose, right? Now, if I ask you one more thing, Can we further simplify this particular ratio over here, which is 6:12:6? Absolutely, we can simplify it. Absolutely, we can simplify it. You just need to divide this ratio by 6. The value comes out to be 1:2:1. Now, if I ask you whether this particular ratio over here, whether it is the actual ratio or simplest whole number ratio, I must say this is the simplest whole number ratio. This is the simplest whole number ratio, correct? Now, if I ask you whether this particular ratio, whether it is simplest ratio or the actual ratio, this is the actual ratio of the atoms. This is the actual ratio of the atoms, correct? That particular formula which gives us the actual ratio of the atoms, that particular formula, you will be calling that as the molecular formula. So I must say, this is the molecular formula of glucose. I must say, the formula which I have written over here, this formula is giving me the actual ratio of the atoms of different elements in glucose. So that formula which gives me the actual ratio of the atoms of different elements, that's something which I call as the molecular formula. As simple as that. Now people, have a look on this particular ratio. This is the simplest ratio. So according to this simplest ratio, what should be the formula? The formula should be C1. The formula should be C1H2O1. The formula has to be C1H2O1. So this particular formula, it is giving me the simplest ratio between the atoms of different elements in case of glucose, and this particular formula I'll be calling as the empirical formula. This is something which I'll be calling as the empirical formula over here, correct? So did you get the difference between what molecular formula is, what empirical formula is? There is something wrong with the pen, by the way. I think I have to use it like this. Yeah, now it's fine. Perfect. So people, I took glucose, right? This particular formula of glucose is giving you the actual ratio of the atoms. And that particular formula which gives us the actual ratio of the atoms, that's what we call as molecular formula. And that particular formula which gives us the simplest ratio of the atoms, that's something which I call as the empirical formula, correct? So this was the molecular formula of glucose. This is the empirical formula of the glucose. Number one, right? Number one. Now, dear students, one more thing which I would want to share with you. And what is that thing? Have a look exactly what I'm going to talk about. Understand properly what I'm going to talk about. If I ask you, what about the molecular mass? What about the molecular mass of glucose? If I ask you what about the molecular mass of glucose, let me tell you, in order to calculate the molecular mass of glucose, you will be taking molecular formula into consideration. From the molecular formula, you will be getting the molecular mass. How exactly? Simple. Molecular mass means sum of atomic masses. Have a look on this particular carbon. Its atomic mass is 12 multiplied by how many carbon atoms? 6 carbon atoms. Plus, what is the atomic mass of hydrogen? 1 AMU. How many hydrogen atoms? 12 hydrogen atoms. In the similar way, what is the atomic mass of oxygen? That's 16 AMU. How many oxygen atoms we have? 6 oxygen atoms. When you solve this particular term, the value comes out to be 180. You can write U or AMU or D. The choice is all yours. Now, if I ask you what is this 180U over here? Since this is now going to be the molecular mass of glucose. So the point is very simple, people. The point is very, very, very simple. Whenever you need to calculate the molecular mass, you have to use the molecular formula. Similarly, whenever you need to calculate the empirical mass, in order to calculate the empirical mass, you will be using the empirical formula, not the molecular formula. Simple, right? Now, if I ask you, calculate the empirical mass of glucose, now you will be using this particular formula. Use this particular formula. Have a look. Carbon, its atomic mass is 12, multiplied by how many carbon atoms? 1 carbon atom, right? Similarly, hydrogen, its atomic mass is 1, How many hydrogen atoms? 2 hydrogen atoms. Similarly, oxygen 16 multiplied by 1. When you solve this, the value comes out to be 30U. Now, if I ask you what this 30U is all about, you will say this 30U, it is not the molecular mass now. It is the empirical mass. Is it simple? So, very, very simple, people. Understand again. I wrote a compound glucose over here, right? One formula is giving me the actual ratio of the atoms. That's what I'm calling as the molecular formula. One formula is giving me the simplest whole number ratio between the atoms. That's what I'm calling as empirical formula. In order to calculate the molecular mass, you'll be using the molecular formula. In order to calculate the empirical mass, you'll be using the empirical formula. Is this much clear to everyone? Let me know once in the chats. Let me know once in the chats if every single thing is clear till here. Yes? Which compound we were talking about? We were talking about glucose, right? We were talking about glucose. Yes? And for glucose, what we got to know? We got to know the molecular formula of glucose is C6H12O6. We got to know the empirical formula of glucose is C1H2O1. We got to know the molecular mass. The molecular mass of glucose is 180U. We got to know the empirical mass of glucose is 30U. So these many things till now we have discussed, right? Now, dear students, I'm going to define a number. I'm going to define a number. I'm going to define a number n over here. Now, you must be thinking what this n is all about. N is simply defined as the ratio of molecular mass of the compound to that of empirical mass. Ratio of molecular mass to that of empirical mass. For example, I'm asking you, what is the n value for glucose? You'll just say the molecular mass of glucose is 180U divided by empirical mass of glucose is 30U. So the n value for glucose is coming out to be 6, right? So n is just a number, n is not moles over here. N is just the number, the ratio of molecular mass to that of empirical mass. N value for glucose is coming out to be 6, right? N value for glucose is coming out to be 6. Now at the same time, I'm writing one more important result. Do remember this. Sometimes in a question we are supposed to calculate the molecular formula. Sometimes in a question they'll ask us how to calculate the molecular formula. Molecular formula is nothing. It is just the empirical formula multiplied by n. Now let's see exactly whether this formula is actually valid or not. Let's see exactly whether this formula is actually valid or not. Let's have a look. What is the molecular formula of glucose? That is C6H12O6 is equal to. What is the empirical formula of glucose? That is C1H2O1. What is the n value for glucose? That is 6. Now this is 6 ones are 6, 6 2 12, 6 1 6. Left hand side, right hand side are coming equal. That means this particular result it's actually valid. This particular result it's actually valid. Okay. Now dear students, there is one more thing which I would want you guys to remember. Then I'll show you what kind of questions can be asked, right? I'll show you what kind of questions can be asked. Have a look. Have a look. Remember one more thing. Remember one more thing. Molar mass of a compound, molar mass is always equal to 2 times the vapor density. Sometimes in a question, they won't be giving you directly the value of molar mass. They will be giving you the value of vapor density. From this vapor density, you just have to multiply the vapor density by 2, which will be given to you in the question. You'll be getting the molar mass. For example, as per the question, vapor density of the compound is given as 30, right? That means you can say the molar mass of the compound is going to be 2 times 30, which comes out to be 60. But now it's molar mass. Now it's molar mass, and its units are going to be grams per mole. But dear students, do we have to use the value of molar mass anywhere, or we have to use the value of molecular mass? We have to use the value of molecular mass. Now let me tell you, in order to convert molar mass into molecular mass, in order to convert the molar mass into molecular mass, what you just need to do is you have to change the units only. It's going to be 60 U. You have to change the units from grams per mole to U. That's all. That's all. Let me know, everyone in the chats, if every single thing is clear till here. Remember, N value. N value is always equal to molecular mass divided by empirical mass. Correct? If molecular mass won't be given to you, then vapor density will be given to you. Vapor density multiplied by 2, that gives me the molar mass. Convert the units, change the units of molar mass, change this grams per mole into U, you'll be getting the molecular mass, right? Once you get the molecular mass, you can get the N value for sure. And once you get the N value, molecular formula can be easily calculated. Did you get it? Give me some green signal from the chats. Give me some thumbs ups in the chats if every single thing is clear. Everyone, people, everyone in the chats. And I can see live watching is 570, 80 around, and likes are only 425. Isn't that the partiality? Yeah? All right. Now let's see exactly how this particular concept is involved in the questions. What kind of questions can be asked? How we can deal with the questions based on molecular and empirical formula. Let's have a look on that now. Understand. Understand properly. The very first question which was asked in your NEET 2021 from the molecular empirical formula. Let's exactly see what the question is all about. The question is, we have got an organic compound which contains 78% by weight of carbon and the remaining percentage of hydrogen. As per the question is concerned, we have got the organic compound which contains two elements. An organic compound contains two elements. One is carbon and one is hydrogen. Correct? The percentage of carbon in the organic compound, the percentage of carbon in the organic compound is 78. The percentage of hydrogen in the same organic compound will be 100 minus 78. That's going to be what? That's going to be 22%. This is something which is given to me. Now there is one thing which is important which you need to know. Understand. We have got an organic compound that contains two elements, carbon and hydrogen. Percentage of carbon in the organic compound is 78. Percentage of hydrogen in the organic compound is 22. Now the point is, what is meant by these percentages? What is meant by this 78% carbon, 22% hydrogen? What is meant by it? It simply tells you, in 100 grams of organic compound, you have got 78 grams of carbon. In the same 100 grams of organic compound, you have got 22 grams of hydrogen. I hope you are able to analyze this. See, we have got an organic compound. It's mentioned that the organic compound has got the percentage of carbon as 78. It simply means 100 grams of organic compound contains 78 grams of carbon. The same 100 grams of organic compound contains 22 grams of hydrogen. Okay? Perfect. Now there are few steps which you need to do. Only few steps which you need to do. And what is that? Have a look. First of all, if I ask you, what about the atomic mass of these elements? Atomic mass of carbon, that's 12 AMU. Atomic mass of hydrogen, that's 1 AMU. Correct? The first step always is to calculate the atomic ratio. That is the first step. First step always is to calculate the atomic ratio. Now, how do you get the atomic ratio? Whatever percentage of carbon is given, divide this given percentage by its atomic weight. So, 78 divided by 12. 78 divided by 12. Whatever value you will be getting from here, that's going to give you the atomic ratio of carbon. Similarly, atomic ratio of hydrogen, it's going to be 22 divided by 1. It's going to be 22 divided by 1. Perfect. So, do remember all these terms which I'm telling you. In order to calculate the atomic ratio, whatever percentage of elements is given, divide the given percentage by their respective atomic weights. Get the atomic ratio. Now, let me see exactly what the atomic ratio we get. we get the value 6.5 and 22. 6.5 and 22. This value is coming out to be 6.5 and this value is coming out to be 22. We got the atomic ratio. We got the atomic ratio. Now the next step will be to calculate the least atomic ratio. Now how do we get the least atomic ratio? Look at these terms which we got here. If I ask you which one is the lesser value among the two, you will say 6.5 is lesser. 6.5 is lesser. Now divide both the terms by the number 6.5. Divide both these terms by the number 6.5. It's going to be 6.5 divided by 6.5. This is going to be 22 divided by 6.5. This value is coming out to be 1. This value will be approximately 3. Perfect. Now, what is this 1 and 3 over here? This is the least atomic ratio. Least atomic ratio. Now, you tell me which formula gives us the idea about the least atomic ratio. Is that molecular formula or empirical formula? Definitely that's empirical formula, right? So, I must say the empirical formula came out to be, it's going to be C1 and H3. C1, H3. This is going to be your empirical formula. Give me some thumbs ups in the charts if you got this. Everyone. Everyone, people, quickly in the chats. Give me some thumbs ups if you got the concept. Now I'm going to take one more question which you guys will be doing with me right now. Yes? Perfectly done. Good job. Let's have a look on one more question then. Alright, similar sort of question. Now I'll be a little quick. See guys, an organic compound contains carbon, hydrogen and oxygen. We have got an organic compound that contains carbon, hydrogen and oxygen. What is the percentage of carbon in the organic compound? It is 38.71%. What is the percentage of hydrogen? It's 9.67%. What is the percentage of oxygen? Percentage of oxygen is going to be simply 100 minus 38.71 plus 9.67. Simple. Simple, right? Completely basics. Carbon percentage is given. Hydrogen percentage is given. So oxygen percentage is simply going to be 100 minus this plus this, correct? Yes, as simple as that. Let's see exactly how much this value comes out to be. This value comes out to be 51.62. So let me write it exactly. This value is coming out to be 51.62. Correct? So the percentage of all the elements in the compound is given to us. Now the first step is to calculate the atomic ratio. How do we get the atomic ratio? Divide the given percentage by its respective atomic weight. So 38.71, you're going to divide it with the atomic weight of carbon, that's 12. 9.67, you're going to divide it with the atomic weight of hydrogen, that's 1. 51.62, you're going to divide it with the atomic weight of oxygen, that's 16. Now, just solve these terms. Let's see what do we get. We get the values over here as 3.23, 9.67, 3.23, right? 3.23, 9.67 and 3.23. What did we get? If I ask you what did we get? Did we get the least atomic ratio? No, we got the atomic ratio. We just got the atomic ratio, right? What are we supposed to calculate? We are supposed to calculate the least atomic ratio. How do you calculate the least atomic ratio? Look at these numbers over here. Which number has got the least value? It's 3.23. Divide every number over here by 3.23. That's all. So it's going to be 3.23 divided by 3.23. It's going to be 9.67 divided by 3.23. And it's going to be 3.23 divided by 3.23. Perfect. So this value comes out to be 1. This value comes out to be 3. This value comes out to be 1. So what did we get now? Should I be calling this as the molecular formula or empirical formula? Dear students, we got the least atomic ratio. And that particular formula which gives me the idea about the least atomic ratio, that's something which I call as the empirical formula. As simple as that. So empirical formula came out to be C1H3O1. C1H3O1. This is something which we were supposed to calculate. Is this clear to everyone? Is this clear to everyone? Let me know quickly in the chats. Everyone, people, everyone, is this clear? Yes? Should I move on to one more concept now? Should I move on to one more concept now? Yes or no in the chats? Yes or no in the chats? I'm damn sure whenever question comes from the empirical formula, you will be able to solve it. Yeah? Perfect? All right. All right, wonderful. Perfect, guys. So let me move on to one more concept then. I hope this is super duper clear to everyone. Calculation of empirical formula. Okay? Now let's deal with the concepts from the chapter's atomic structure. Let's deal with the concepts from the chapter atomic structure. There are many concepts in the atomic structure, but I'll be giving you some 5 to 6 top-notch concepts from which the questions are going to come in your NEET examination from this chapter atomic structure. Okay? Let's have a look on the first concept. Understand. Understand, guys. First of all, we are going to talk about the Bohr's model, right? We are going to talk about the Bohr's model. Let me tell you this particular Bohr's model, the first thing. It is applicable only to single electron species. It's applicable only to single electron species. Now, what are single electron species? Single electron species are the ones which just contain one electron. Like, you have got hydrogen, which contains only one electron. You have got He positive, contains only one electron. You have got Li di positive, containing only one electron. So, any species which just contains one electron, we call it as the single electron species. And my dear students, this Bohr's theory, Bohr's model, it's applicable only to single electron species. The first question which is asked from the Bohr's theory, that is related to radius. That is related to radius. This is the first question which you will be getting. Now understand and remember. Let's say I have got a single electron species whose nucleus I'm mentioning. This is the nucleus of the single electron species. Let's say we have got the electron which is revolving in this particular shell. This is the electron. This is the electron here, right? This is the electron. Perfect. We have got a single electron species whose nucleus I have mentioned, whose electron I have mentioned. I'm assuming the atomic number of the species which we have taken, let's assume that's Z. Z denotes the atomic number of the species. It denotes the atomic number of the species. Let's assume the electron which is revolving in this shell. Let's say the electron is revolving in nth shell, right? Let's call the shell number as the nth shell. Perfect. Let's call the shell number as nth shell. So I'm saying the electron is revolving in the nth shell of the single electron species whose atomic number is Z. Now if I ask you, tell me the radius of this Bohr's orbit. Tell me the radius of this Bohr's orbit. The radius of this particular Bohr's orbit I'm representing with Rnth. I'm asking you, what is the radius of the orbit in which electron is revolving? There is one simple result which you need to remember. What is that? Radius of nth Bohr's orbit. It's equal to R naught n square divided by Z. One simple result you need to remember. Radius of nth Bohr's orbit is equal to R naught n square divided by Z. Yes? Now, dear students, what this R naught is? R naught is a constant whose value is simply 0.529 angstroms. 0.529 angstroms. So, the first result which I would want you guys to remember, that's this one. What is this N? It is the shell number in which electron is revolving. What is this Z? This is the atomic number of the single electron species which we are taking into consideration. Okay? Now, dear students, one more thing. I'll show you exactly the application part of this formula in a while. One more thing which I would want you guys to share with you. What is that? Have a look. See guys, for example, let's say I have got two single electron species, right? Or let's just take two single electron species. One is going to be, right? One is having the atomic number of Z1. Let's say the electron in this single electron species is revolving in shell number N1. Let's say the radius of the electron in this particular Bohr's orbit is R1, right? Similarly, I've got one more single electron species whose atomic number is Z2. The shell number in which electron is revolving, that's N2. The radius of this orbit is R2. I hope you're getting. I took two single electron species. Two single electron species. I'm assuming the electron in the first single electron species is revolving in the orbit number of N1. The radius of this orbit is R1. The atomic number of the single electron species is Z1. Similarly, one more. I told you a few minutes back, radius of nth Bohr's orbit, that's just equal to R naught n square divided by Z. So can I say radius, it's directly proportional to n square, inversely proportional to Z. Now the question is asked, compare the radius of these two Bohr's orbits. So you are just going to write R1 divided by R2 is equal to R1 divided by R2. It's going to be N1 square, it's going to be N2 square, and it's going to be Z2 divided by Z1. Whenever question like this comes, you're going to use this particular result. Okay? Compare the radius of two Bohr's orbits. Compare the radius of two Bohr's orbits. This is the result which you guys will be using. Right? Let's solve few questions so that you can understand what kind of questions can be asked from the radius. Okay? I'm giving you one simple question. Let's see if you can solve this question or not. One simple question I'm giving you. Give it a try. Give it a try, my dear students. Everyone, give it a try. The question is, the Bohr's orbit radius for hydrogen atom. So first of all, we are given with hydrogen. Right? Now we are given with the first orbit. N is equal to 1 for hydrogen. So for hydrogen, the orbit number is given as 1. Okay? Now for hydrogen, we know the atomic number. That's also 1. Right? The radius of the first Bohr's orbit of hydrogen, which I'm representing with R1, it's also given to me as 0.530 angstroms. Correct? Now on another side, what are we supposed to calculate? The radius for the first excited state. The radius of the first Bohr's orbit is given. We are supposed to calculate the radius of the first excited state. First excited state means n is equal to 2. So basically, for hydrogen only, now we have to calculate the radius of the second Bohr's orbit. We have to calculate the radius of the second Bohr's orbit. Atomic number is going to remain same. We have to calculate the radius of second Bohr's orbit. Correct? One formula I gave you a few minutes back only. What was that? That was R1 divided by R2 is equal to N1 square. This was N2 square. This was Z2. This was Z1. The question is done and dusted. R1 value, that's 0.53 divided by R2 value, we need to calculate, is equal to N1 square, that's 1 ka square is 1, divided by N2 square, 2 ka square is 4, Z2 divided by Z1, 1 by 1 that's 1, correct? 1 by 1 that's 1. So have a look on this particular equation. Can I say I got one equation which only contains one variable? So from here, can you calculate the value of R2? Can you calculate the value of R2? Absolutely. So I can see majority of the people are coming up with option 4. Is that? So when you cross multiple, you'll be getting the R2 value exactly as 2.12 angstroms. Now let me know, everyone in the chats, if this concept is clear to everyone. Everyone, people, everyone. Let me know quickly in the chats if you can solve the questions based on this. With the thumbs ups. With the thumbs ups, quickly. Everyone. Perfect, guys. Wonderful. All right then. One more question from the same concept which was asked in NEET 2022. Look at the question carefully. If the radius of second Bohr's orbit, of He positive is 105.8 picometers, what is the radius of third Bohr's orbit of Li positive? So two single electron species are given to us, right? One is your He positive, and one more is your Li positive. These are the two single electron species which are given to us, correct? Two single electron species which are given to us. If the radius of second Bohr's orbit, of He positive is given to us as 105.8 picometers. If I ask you what is the atomic number of helium, that's 2, correct? If the atomic number of helium is 2, that means the atomic number of He positive will be also 2. As simple as that. What is the radius of third Bohr's orbit? Of Li positive? So R2 value we have to calculate. Now if I ask you what is the atomic number for this Li positive, hydrogen, helium, lithium, the value is 3, right? The formula which I gave you a few minutes back, you just use that and kill the equation. That's all, right? So compare the radius. R1 divided by R2 is equal to N1 square divided by N2 square multiplied by Z2 divided by Z1, correct? R1 value is 105.8. R2 you need to calculate is equal to N1 ka square, 2 ka square that's 4, N2 ka square, 3 ka square that's 9, Z2 divided by Z1, 3 divided by 2, correct? So this is 3, 1, this is 3, 3, perfect. This is 2, 1, this is 2, 2, perfect. So you got the value as 105.8 divided by R2 is equal to 2 divided by 3. Look at this particular equation. One equation, one unknown. So from this equation, can't we get the value of R2? Isn't it simple and basic? Everyone in the chats? After solving this particular equation, you'll be getting the answer exactly as 158.7 picometers. A very simple and basic thing, right? So these are the questions which can be asked from the radius. Okay? One more question. This is going to be your homework question. This is your homework question from the same concept. And I would want everyone to solve this question and write its answer at the end in the comment section. Right? I'll personally check the comment section today. I'll see exactly how many questions marked, how many students marked this question right. And tomorrow I'll show you the results on the slide itself over here. Right? This is your homework question. Do let me know its answer in the comment section at the end of the session, right? This is your homework question and its result will be shown tomorrow in the form of a slide over here, okay? Now people, let's move on to the second concept in atomic structure. Second concept, calculation of velocity. Let's say I have got a single electron species whose nucleus is this, right? Let's say this is the electron which is revolving in this particular Bohr's orbit. This is the electron. Perfect. Now this particular electron will be moving with some velocity basically. Now the questions are asked to calculate the velocity of the electron which is moving in this particular Bohr's orbit. I'm assuming this Bohr's orbit is the orbit nth, right? I'm assuming the single electron species which we are talking about, its atomic number is Z. Now the velocity with which the electron will be moving, it is given by this particular result. V0 multiplied by Z divided by N. This V0 is a constant whose value is 2.18 into 10 raised power 6 meter per second. Isn't it simple? Do remember this particular result, my dear students. Calculation of velocity of an electron in any Bohr's orbit. Perfect. Now, dear students, whenever you need to compare the velocity of two electrons moving in two different Bohr's orbits, whenever you'll be asked to calculate the velocity, whenever you need to calculate the ratio of the velocities of the electrons moving into different orbits, what you'll be doing at that time? You'll just write V1 divided by V2 is equal to Z1 divided by Z2, and this is going to be N2 divided by N1. Isn't it simple? Simple and basic stuff I'm teaching you. I'm not teaching you some hi-fi stuff over here. Yeah? Correct? This is how you compare the velocities of two electrons in two different Bohr's orbits of two different single electron species. Now let's see exactly how these two formulas are used. Let's start with a question. Let's start with a question. Look at this particular question, guys. Can you solve this? Calculate the velocity of the electron placed in the second orbit of Li di positive. So basically we are given with Li di positive. We are given with Li di positive. This is the single electron species that's given. Now tell me, what about the atomic number of lithium? Atomic number of lithium is 3. Hydrogen, helium, lithium. Right? The electron is present in the second orbit. The electron is present in the second orbit. Right? What do we need to calculate? We need to calculate the velocity of this particular electron. And we know velocity of the electron in the nth Bohr's orbit, it's equal to V naught multiplied by Z divided by N. What is the value of V naught? V naught value is 2.18 into 10 raised power minus 6. Z value, the atomic number is 3, and N value, that's 2. Solve it, you'll be getting the answer, this 10 raised power 6, not minus 6, sorry. Okay, solve it, get the answer in meter per second. So I can see majority is coming up with option 4. Is option 4 the correct answer? So when you solve this, you'll be getting exactly the option 4, which is going to be the correct answer of this particular question. Simple and basic again. And this is again the short question which will be asked. I'm moving on to one more question. Let me see if you can solve this or not. Let me see if you can solve this or not. Have a look on this particular question based on the same concept. Absolutely, guys, wonderful. It's option 4. If the velocity of the electron in the first orbit of hydrogen atom, so we are given with hydrogen atom, its atomic number is 1, right? The electron is present in the first orbit. The electron is present in the first orbit. The velocity of electron in the first orbit is given to us as V, right? What will be the velocity V2 of an electron in third orbit of Li di positive? So we have got Li di positive as well. Its atomic number, hydrogen, helium, lithium, it's 3. In which shell the electron is moving? The electron is moving in the third orbit. N2 is 3. We need to calculate the V2 value. Can you let me know what should be the answer? Can you let me know what should be the answer? Can you let me know exactly what should be the answer? Quickly. Quickly, guys. So simply you will be doing one thing. You will be comparing the velocities, right? You will be writing V1 divided by V2 is equal to Z1 divided by Z2 multiplied by N2 divided by N1. So V1 divided by V2 is equal to Z1 Z2, Z1 Z2. So 1 divided by 3 multiplied by N2 by N1, N2 N1. So 3 divided by 1. So you are getting, instead of V1 I'm writing V. V divided by V2 is equal to 1. So from this particular equation, you got to know V2 is equal to V. Is it done? Done and dusted, right? So what can you conclude from here? What can you conclude from here? You got to know whatever is going to be the velocity of the electron in the first orbit of hydrogen, same is going to be the velocity of the electron in the third orbit of Li di positive. That's something which we got to know, right? Again, a very simple and basic concept this was. Yes? Perfect. Everyone, let me know in the chats with the thumbs ups. Quickly, guys. Quickly, everyone, quickly. Everyone, quickly. Perfecto. Done and dusted, yeah? Let's have a look on the third concept which can be asked. Questions based on time period. Till now, I showed you exactly how to compare the radius of two different Bohr's orbits, how to compare the velocity of the electrons moving in two different Bohr's orbits. Now, it is the time to compare the time periods of electrons in two different Bohr's orbits. Time period basically, right? Let me tell you, time period of electron in the nth Bohr's orbit. that's directly proportional to n cube, inversely proportional to z square. Something which you need to remember, that's all. Something which you need to remember. Time period of the electron in the nth Bohr's orbit, it's directly proportional to n cube, inversely proportional to z square. Now, if you need to compare the time period of electrons in two different Bohr's orbits, you'll be simply using the formula T1 divided by T2 is equal to N1 cube, N2 cube, Z2 square, Z1 square. A very simple and basic question this was. Right? Perfect. Directly proportional to n cube, inversely proportional to z square. And I'm sure you can easily apply it in the questions. The way we applied the results in case of radius and velocity, in the similar way you are going to apply this result. Similarly, if they ask you to calculate the frequency of the electron in the nth Bohr's orbit, frequency of the electron in the nth Bohr's orbit, that's going to be directly proportional to z square, inversely proportional to n cube. So if you want to compare the frequencies, it's going to be mu1 divided by mu2 is equal to z1 square. This will be z2 square, and this is going to be n2 cube. This is going to be n1 cube. This is going to be n1 cube. This is how you compare the frequencies as well. So questions can be asked out of these two as well. Yeah? Clear? Clear to everyone? Let me know in the chats quickly. Let me know in the chats quickly, people. Is it super clear to everyone? Yeah? Wonderful. So till now, we have discussed about the radius, velocity, comparison of time periods, comparison of frequencies. Now, there are questions based on energy as well. There are questions based on energy as well. Let me give you those questions. Let me give you those questions. By the way, this constant T naught, that's 1.5 into 10 raised power minus 16 seconds. Okay, this is the value of T naught. Basically, I gave you the result. I gave you the result as time period of the nth electron in the nth Bohr's orbit, that's directly proportional to n cube. So if you remove the proportionality sign, there will be a constant T naught, and the value of that particular constant is 1.5 into 10 raised power minus 16 seconds. Right? I hope this is clear. Perfect. Now, guys, the question based on energy, right? Let's say I've got a single electron species X, or let me not write it as X. Let's say I've got some single electron species whose nucleus is this. This is the electron moving in the orbit number of n. The electron is moving in the nth orbit, nth Bohr's orbit. Let's say the atomic number of this particular species is Z. Let's say the atomic number of this particular species is Z. Now, if I ask you, what about the energy? What about the total energy possessed by this electron? When the electron is moving in the nth Bohr's orbit, when the electron is moving in the nth Bohr's orbit, what will be the total energy possessed by the electron in the nth Bohr's orbit? Simple. I'm writing total energy, okay? Let me write it completely. The total energy possessed by the electron in the nth Bohr's orbit is equal to minus 13.6 Z square divided by n square electron volts. Total energy possessed by the electron in the nth Bohr's orbit, that's equal to minus 13.6 Z square divided by n square electron volts. Now, if I ask you, what about the kinetic energy possessed by the electron? What about the kinetic energy possessed by the electron in the same nth Bohr's orbit? Just change the sign, rest everything same. 13.6 Z square divided by n square electron volts. Simple and basic. If I ask you, what about the potential energy possessed by the system? What about the potential energy? It's going to be simple. Minus 27.2 Z square divided by n square electron volts. These are just three results which you need to remember about the energy. As simple as that. The total energy possessed by the electron in the nth Bohr's orbit, kinetic energy possessed by the electron in the nth Bohr's orbit. In the similar way, the potential energy, which is minus 27.2 Z square divided by n square. Now, if you ask me, what kind of questions are asked from this particular energy, right? What kind of questions are asked? Before that, let me tell you one more thing. For example, a question is asked. You are given with two single electron species. There are two electrons moving in these two single electron species in two different Bohr's orbits. Compare their total energies. Total energy is directly proportional to z square, inversely proportional to n square. Compare the total energies of the electrons present in two different Bohr's orbits. How you are going to do that? Simple. E1 divided by E2 is equal to what? It's going to be Z1 square divided by Z2 square multiplied by N2 square divided by N1 square. Right? This is the result which you guys will be using. That's all. Done and dusted. Yes? Let's try to solve certain questions so that it becomes properly clear to you. Okay. Look at this question. Dear students. The energy of the second Bohr's orbit, of hydrogen atom. So basically you are taking hydrogen atom. You are given with the second Bohr's orbit. So N1 is 2. Second Bohr's orbit. Total energy of the electron in the second Bohr's orbit is minus 328 kilojoules per mole. The energy of the fourth Bohr's orbit would be, for the same hydrogen, what is the energy of the electron in the fourth Bohr's orbit? E2 value you need to calculate. Since the element is same, atomic number is 1, here also the atomic number is 1. Correct? Will you be able to solve this question? I told you a few minutes back only. Energy of the electron, total energy possessed by the electron in the nth Bohr's orbit, that's minus 13.6 z square divided by n square. Right? So you'll be using this particular result. E1 divided by E2 is equal. Minus 13.6 z square divided by n square. So it's going to be z1 square divided by z2 square multiplied by n2 square divided by n1 square. All the values are given. You just need to calculate the E2 value. Rest everything is given to you. Simple and basic again. Yes? Perfect. Let me know once in the chats if you can solve this sort of a question quickly. Everyone in the chats, quickly. Quickly, guys. Everyone quickly. Absolutely, right? So look at this particular question. This is one more question based on the same concept. According to Bohr's theory, the energy required for an electron in Li di positive ion to be emitted from n is equal to 2 state is. So first of all, as per the question is concerned, we are given with Li di positive, right? Whose atomic number is 3. The electron is present in the second orbit. If I ask you how much energy is possessed by this electron, you will say minus 13.6 z square divided by n square, right? So it's going to be minus 13.6, 3 square is 9, divided by 4, these many electron volts, correct? This is something which you guys are going to say. So basically, I'm talking about Li di positive. Let's say this is the nucleus of Li di positive. This is shell number 1, this is shell number 2, this is shell number 3. Similarly, this is the infinite shell. Right? The electron is present in the shell number 2. The electron is here. It is under the influence of the nucleus. Now, as per the question is concerned, how much, and since this electron is under the influence of the nucleus, if you want this electron to be taken out of the influence of the nucleus, you have to supply energy, right? Now, how much energy has to be supplied to take this electron out from the influence of the nucleus? So basically what you have to do is, you have to do simple one thing. You have to make sure the electron moves from n is equal to 2 to n is equal to infinity. You have to make sure the electron moves from n is equal to 2 to n is equal to infinity. Because when electron reaches the infinite energy state, that means the electron is out of the influence of the nucleus. Correct? Perfect. So if I ask you, how much energy has to be supplied in order to make sure the electron goes from 2 to infinity? So we have to make sure the electron goes from 2 to infinity. How much energy has to be supplied? Whatever is the energy gap between these two shells, whatever is the energy gap between these two shells, same amount of energy you have to supply. As simple as that. Same amount of energy you have to supply. Perfect. What is the, I'm asking you, how much energy we need to supply? Whatever is the energy gap between these two shells, which I'm representing with delta E, which will be equal to E infinity minus E2. E infinity. E infinity is always 0, you know, it is 0 minus. E2 value you have calculated, minus times 13.6 into 9 divided by 4. It's minus 13.6 into 9 divided by 4. Just solve it. This is going to be the value. This is going to be the value. These many electron volts you have to provide, then only you can make sure the electron moves from n is equal to 2 to n is equal to infinity. So basically, in order to take the electron out of the influence of the nucleus, this much energy you have to supply, right, in this particular scenario. Let me know once in the chats if it is clear to everyone. Everyone, quickly. Perfectly done. So the answer of this particular question is going to be 30.6 electron volts. Wonderful. Now, dear students, there is one more concept which is asked about the spectral lines. About the spectral lines. We know when the electron moves from higher energy state to lower energy state. When the electron moves from higher energy state to lower energy state, energy is emitted by the electron, right? Energy is emitted by the electron in the form of electromagnetic radiations. That's something which you all must be knowing. Whenever the electron makes a transition from higher energy state to the lower energy state, energy is emitted by the electron in the form of electromagnetic radiations. Right? Right? You know it. Now people, the question arises. The question arises. Since we know when the electron makes a transition, from higher energy state N2 to lower energy state N1, energy is emitted in the form of electromagnetic radiations, right? Now, what is the wavelength of that electromagnetic radiation which is emitted when electron makes a transition from N2 to N1? N2 is basically your higher energy state and N1 is your lower energy state. The question is asked, what is the wavelength of the photon? What is the wavelength of the electromagnetic radiation which is emitted when the electron makes a transition from higher energy state to low energy state? For that purpose, we use the Rydberg's formula. For that purpose, we use the Rydberg's formula. And what is the Rydberg's formula all about? 1 divided by lambda is equal to R Z square 1 upon N1 square minus 1 upon N2 square. This is one more important result which I would want you guys to remember. This is the formula used to calculate the wavelength of the electromagnetic radiation which is emitted when the electron makes a transition from higher energy state to the lower energy state. Okay? Higher energy state to the lower energy state. Now people, one more thing which I would want you guys to remember. This R stands for Rydberg's formula, Rydberg's constant. Okay? Do remember, just to simplify the calculation, 1 divided by R value is equal to 911.5 angstroms. This is something which I would want you guys to remember as well. Okay? Now comes a point. See, understand and analyze things. Lyman series everyone would have heard. Lyman series everyone would have heard. When the electron makes a transition from higher energy state to shell number 1, we get a series of lines. That series of lines is what we call as Lyman series. Right? So electron makes a transition from higher energy state to shell number 1. To shell number 1. It can be 2 to 1, 3 to 1, 4 to 1, 5 to 1, etc., etc., right? Similarly, if you talk about Balmer series, the electron makes a transition from higher energy state to shell number 2. It can be 3 to 2, 4 to 2, 5 to 2, 6 to 2, etc. Paschen series. The electron makes a transition from higher energy state to shell number 3, right? Like 4 to 3, 5 to 3, 6 to 3, etc. Lyman-Balmer Paschen, now it's going to be bracket, then it's going to be fund, right? In bracket series, the electron makes a transition from higher energy state to shell number 4. In fund series, it's going to be higher energy state to shell number 5. So basically, one thing which I have to make you guys remember here, that the ground state in case of Lyman series and as is shell number 1, the ground state in Balmer series is shell number 2, the ground state in Paschen series is shell number 3, ground state here is 4, ground state here is 5. Correct? Right? Now people, why I'm telling you all this? All the lines which we get in Lyman series, all the electromagnetic radiations which we get in Lyman series, they fall into ultraviolet region. All the Lyman series radiations which we get, the radiations which we get in the Lyman series, they fall into ultraviolet region. Balmer series, they fall into visible spectrum. This is going to be infrared. This is going to be infrared. This is going to be infrared as well. Okay? Perfect. Do remember this particular scenario as well. Do remember this particular thing as well. This is important. Your Lyman series, it falls into ultraviolet region. Balmer series falls into the visible region. Paschen series falls into infrared. Bracket series, it falls into infra. And similarly, your fund series, it again falls into infrared region only. This question can be asked, right? Now comes the point. For example, I'm trying to analyze the Lyman series a bit. Let me analyze the Lyman series a bit, right? Lyman series, in which the electron makes a transition from higher energy state to shell number 1. Higher energy state to shell number 1. If I talk about the first line of Lyman series, which is also called as H alpha line of Lyman series, what does that mean? In case of Lyman series, the electron makes a transition from higher energy state to shell number 1. Correct? Now I'm talking about the first line of Lyman series. First line means the transition is going to be from 2 to 1. Second line means the transition is going to be from 3 to 1. Third line of Lyman, 4 to 1. I hope you're getting it. First line of Lyman series. Lyman series, the electron makes a transition from higher energy state to shell number 1. Now I'm talking about the first line of Lyman series. First line means the electron is making a transition from 2 to 1. The electron is making a transition from 2 to 1. So the higher energy state over here is 2. This is the higher energy state. This is the lower energy state. And you know higher energy state is represented by N2. Lower energy state is represented by N1. Correct till here? Now dear students, since the electron is making a transition from 2 to 1, higher energy state to lower energy state, it's going to emit radiation. What is the wavelength of that emitted radiation? Use the Rydberg's formula. 1 divided by lambda is equal to R. Z value, since we are talking about hydrogen, Z ka square is 1 ka square. 1 upon N1 square, 1 upon N1 square, minus 1 upon N2 square. The value comes out to be 4. So this value is 1 divided by lambda is equal to R, and it's going to be 4 minus 1, 3 divided by 4. Now if you take the reciprocal of this particular equation, you get lambda is equal to 4 divided by 3 multiplied by 1 by R. Now I told you a few minutes back, 1 by R is nothing, that is 911.5, and this is going to be angstroms. Now if you ask me what did you calculate? If you ask me what did I calculate? What is it? This is the wavelength of the photon which is emitted when the electron makes a transition from 2 to 1 in case of hydrogen. This is the wavelength of the photon which is emitted in case of H alpha line of Lyman series. This is the wavelength of the photon which is emitted in the first line of Lyman series. Correct? Correct, guys? Isn't it simple? Isn't it simple? Let me take one more case. Let me see if you can solve that as well. For example, I'm talking about the first line, or let's say I'm writing second line. Second line of Balmer series. Second line of Balmer series, okay? Second line of Balmer series. Now analyze things. In case of Balmer series, the electron makes a transition from high energy state to shell number 2. So electron has to come to shell number 2. The electron has to come to shell number 2. This shell number 2 is going to be the ground state, which I'm representing with N1. So electron is finally coming to 2. Now they are asking about the second line. First line means 3 to 2. Second line means 4 to 2. So the transition has to be from 4 to 2. So this is the higher energy state N2. Now we got to know in case of second line of Balmer series, the electron is making a transition from 4 to 2. So definitely the electron is making a transition from high energy state to low energy state. Energy will be emitted in the form of electromagnetic radiation. Now what about the wavelength of that electromagnetic radiation which is emitted? Again use the Rydberg's formula. 1 divided by lambda is equal to R Z square 1 upon N1 square minus 1 upon N2 square. Correct? So it's simply going to be 1 divided by lambda is equal to R. Z square for hydrogen is 1. 1 upon N1 square is 2 2s are 4 minus N2 ka square is 16. 4 ka square is 16. Now solve it a bit. It's going to be 1 divided by lambda is equal to R. It's going to be 16 minus 4, that's 12, divided by 64. If you take the reciprocal of this particular equation, what do we get? You get lambda value as 64 divided by 12 multiplied by 1 by R, right? So you can write it as 64 divided by 12, 1 by R value, you know that's 911.5. The answer is going to be in angstroms. As simple as that. Quickly let me know in the chats if it's clear. Quickly let me know in the chats if it is clear. Yes? Someone is saying why not 3 to 2? Since we are talking about the Balmer series. In the Balmer series, the electron has to reach shell number 2, right? So this is for example shell number 3, this is 4, this is 5, this is 6, correct? The electron has to reach here. Now 3 to 2 means first line, 4 to 2 means second line, 5 to 2 means third line of Balmer, fourth line of Balmer, etc., right? Perfect. This is N1 ka square. N1 is 2, so 2 ka square comes out to be 4. This is N2 ka square. N2 is 4, so 4 ka square comes out to be 16. Then you can solve. Rexnite, you can use that, absolutely. No issues at all. Now, dear students, there is one more thing. Since you got to know about like how to calculate the wavelength of the electromagnetic radiation emitted, right? Now, there is one more thing which can be asked. The calculation of spectral lines. Calculation of spectral line, which is all about the formula based. It's all formula based. Total number of spectral lines. This question is asked frequently. Total number of spectral lines. Total number of spectral lines obtained when the electron makes a transition from higher energy state N2 to lower energy state N1. Total number of spectral lines obtained when the electron makes a transition from higher energy state N2 to lower energy state N1. It's given by a simple result. What is that result? Remember that from now onwards. It's N2 minus N1 multiplied by N2 minus N1 plus 1 divided by 2. But do remember this particular result. It's valid for larger number of atoms. It's valid for larger number of atoms. Now understand what I'm going to say. Yes, I'm going to teach you the quantum mechanical part as well. Just wait. Have a look. For example, dear students, I'm telling you, in case of hydrogen, the electron is making a transition from 5 to 1. The electron is making a transition from 5 to 1, correct? So higher energy state I'm going to represent with N2, lower energy state I'm going to represent with N1. Now the question is asked, calculate the total number of spectral lines. Total number of spectral lines obtained. Use the formula, that's it. Total number of spectral lines obtained. It's going to be N2 minus N1. So 5 minus 1, that's 4. Multiplied by N2 minus N1 plus 1. 5 minus 1 plus 1, that's 5. Divided by 2. The value comes out to be 10. So basically you got to know there are in total 10 spectral lines which are produced when the electron is making a transition from 5 to 1. Now if I ask you, out of these total 10 spectral lines, how many spectral lines will fall into Lyman category? How many spectral lines will fall into Balmer category? How many in Paschen? How many in bracket? How many in fund? How you can calculate that? How you are going to calculate that? See, you got to know one thing. Since the electron is making a transition from 5 to 1, so total 10 spectral lines are observed. Total 10 spectral lines are obtained. Out of these 10 spectral lines, how many will fall into Lyman? How many in Paschen? How many in Balmer? Etc. How to do that? One simple result which you are going to remember from now onwards. I'm writing the number of spectral lines falling into Lyman series, falling under Lyman. If this is the question, then the answer is going to be higher energy state N2 minus the lower energy state of Lyman series. The lower energy state of Lyman series. Now what that means? Higher energy state, since the electron was coming from 5 to 1, so higher energy state is 5. Higher energy state is 5 minus lower energy state of Lyman series. In case of Lyman series, what is the lower energy state? The electron reaches n is equal to 1 at the end. Lower energy state in case of Lyman is 1, so 5 minus 1 comes out to be 4. So out of 10 spectral lines, there are 4 spectral lines which come under Lyman category. Right? Similarly, if I ask you, how many spectral lines come under Balmer category? How many spectral lines come under Balmer category? Again, it's going to be higher energy state N2 minus the lower energy state of Balmer. The lower energy state of Balmer. Simple. What was the higher energy state from where electron was coming? Electron was coming from the 5th shell. What is the lower energy state of Balmer? In case of Balmer, the electron finally reaches n is equal to 2. So 5 minus 2. That comes out to be 3. So out of the 10 spectral lines, there will be 3 spectral lines which come under the Balmer category. Right? Yes? Similarly, how many spectral lines fall under the category of Paschen? How many spectral lines falls under the category of Paschen? It's going to be N2 minus lower energy state of Paschen, Lyman, Balmer, Paschen, n is equal to 3. So 5 minus 3 comes out to be 2. Similarly, Paschen, then comes your bracket. Bracket, the answer is going to be 1. Correct? So there were in total 10 spectral lines. Out of 10 spectral lines, 4 are falling under Lyman category, 3 are falling under Balmer, 2 are falling under Paschen, 1 is falling under bracket. If you take the sum of these, 4 plus 3 plus 2 plus 1, the value comes out to be 10. In total, there were only 10 spectral lines, right? Out of which 4 are falling into Lyman category, right? 3 are falling into Balmer category, 2 are falling into Paschen category, and 1 is falling under bracket category. I hope this sort of a question you can easily solve from now onwards, right? Let me know once in the chats with the thumbs ups if it is clear. Everyone. Let me know once in the chats, people, if it is super duper clear to everyone. If this is clear to everyone, tell me the answer of this question right now. Right now in the chats. I want to see who is going to be the first one to answer this question. When an electron is excited from ground state to 5th orbit, the number of spectral lines. Ground state means the lower energy state is 1. Higher energy state is 5. What is going to be the answer? Quickly. Quickly, everyone. Quickly, quickly. Quickly means quickly. Answer of this question. The electron is making a transition from 5 to 1. Total spectral lines N2 minus N1 into N2 minus N1 plus 1 divided by 2. This question we solved 5 minutes back only. The answer was 10, right? This is the question which we did. Okay, let me see how much you are remembering with me. If this question comes in your exam, what should be your answer? Which of the following series of transition in the spectrum of hydrogen falls in visible region? Which category, which series falls under visible? Which series falls under visible category? Tell me in the chats quickly. Tell me in the chats quickly. Few minutes back I told you, Lyman falls into ultraviolet, Balmer invisible, Paschen infrared, Brackett infrared, Fund infrared. The answer is going to be absolutely killed it. Wonderful. Good job, good job, good job. Now, dear students, one more question which is frequently asked in your NEET examination from the same chapter. That is from the concept of node, right? Concept of node. Now, guys, have a look. Understand and remember. If I ask you one thing, how many quantum numbers we have? We have 4 quantum numbers, you know it. Principal, azimuthal, magnetic, spin. We have 4 quantum numbers in total, right? Out of 4 quantum numbers, the first question that can be asked, how many quantum numbers are basically the outcome of Schrodinger's wave equation? Out of the 4 quantum numbers, how many quantum numbers are the outcome of Schrodinger's wave equation? 3 quantum numbers. One is principal, one is azimuthal, one is magnetic. These 3 are the outcome of Schrodinger's wave equation. Point number 1. Point number 2. This N represents your principal quantum number, L represents azimuthal, M represents magnetic, right? Do remember one more thing, the value of L. It is from 0 to N minus 1. The value of L, it's taken from 0 to N minus 1. The value of M, it's taken from minus L to plus L. Minus L to plus L. Spin quantum number, S can have 2 values, either plus 1 by 2 or minus 1 by 2. This is something which every one of you would be knowing. I'm damn sure about that, right? I'm damn sure about that. Now, dear students, if I talk about the S subshell, in case of S subshell, what is the value of L? What is the value of azimuthal quantum number? It's 0, right? For S subshell, the value of L is 0. If I talk about the P subshell, for P subshell, the value of L is 1. D subshell, the value of L is 2. F subshell, the value of L is 3. This is something which every one of you must be knowing, correct? Now, dear students, a very simple and basic question is asked, which is directly formula based. That is related to the calculation of nodes. First question is asked to calculate the total number of nodes in an orbital. Total number of nodes. Total number of nodes are calculated by the formula n minus 1. This is the formula by means of which we can calculate total number of nodes, right? Node means the region or the plane where the electron density is 0, where psi square value is 0. I'm not going into the details. I'm just telling you how to solve the question quickly. That's all, nothing else. If you need to calculate total number of nodes, you have to use the result n minus 1. If it is asked to calculate, spherical or radial nodes. If you are asked to calculate spherical or radial nodes, spherical or radial nodes are calculated by the result n minus L minus 1. This is the result, n minus L minus 1. This is the formula by means of which you can calculate the spherical or radial nodes. The third one, that is angular nodes. Angular nodes are calculated by the result by the value of L. For example, I'm writing 2s orbital. I'm writing 2s orbital. In case of 2s, what is the value of principal quantum number n? N value is 2. Since it's S subshell, the value of L for S subshell is 0. If I ask you the total number of nodes, that's going to be n minus 1. That's going to be 2 minus 1, that means 1. If I ask you how many angular nodes are there, angular nodes are given by the value of L. L value is 0, so angular nodes are 0. If I ask you, in case of 2s, how many radial or spherical nodes are there? N minus L minus 1. 1 minus 0 minus 1. The value comes out to be 1. Right? Direct questions are asked from these particular 3 formulas. That's it. Nothing else. Can you solve the questions based on 3 formulas? Yes or no in the chats quickly? Yes or no in the chats quickly, guys? Everyone? Can you solve this particular question? Okay, let me teach this a bit more in detail. But before going into the details, as per you, what should be the answer of this question? NEET 2020. What should be the answer of this question? Then I'll teach this a bit more in detail. Quickly, guys, everyone, I want the chat box to quickly jump fast. Yes, I'm going to show you the graphs as well. Just wait. Tell me the answer of this question. The question is the number of angular nodes and radial nodes in case of 3s. So we are given with 3s. Perfect. What is the value of principal quantum number n? N value is 3. What is the value of azimuthal quantum number for s? It's 0. How many total number of nodes will be there? N minus 1. 3 minus 1, that comes out to be 2. How many angular nodes will be there? The value of L value is 0. How many spherical or radial nodes will be there? N minus L minus 1. N minus L minus 1. The value comes out to be 2. That's going to be your answer. Correct? Simple and basic. You should be able to solve this question. All right. What about this one? Quickly. What should be the answer of this question, everyone? Everyone in the chats. Orbital having 3 angular nodes and 3 total nodes. Everyone, quickly. What should be your option as per this? Orbital is having 3 angular nodes. Orbital is having how many angular nodes? 3 angular nodes. Angular nodes are calculated by the value of L. So L value is 3. L is 3 basically for F subshell. Correct? There is only one F subshell which is given. That's 4F. Done and dusted. Yeah? Correct? Absolutely. Now I'm going to teach you something important, which has never come in NEET examination yet. So the probability of that question to be asked in the NEET is more. Okay? Let's have a look on that. Understand what I'm going to teach now. That's important. Okay? Now, people, I'm going to give you directly the shortcuts. I'm not going into the details. Simple shortcuts so that you can solve the question quickly. That's going to be psi square versus R graphs and psi versus R graphs for S and P orbitals. Right? Now, guys, understand. Let me start with the first example. Let's say I'm starting with, for example, 2s. Let's say I've got 2s subshell, 2s orbital I have, right? I've got 2s. In case of 2s, what is the value of principal quantum number? That's 2. What is the value of azimuthal quantum number? That's 0. If I ask you how many total nodes are there? total nodes, n minus 1, 2 minus 1, that's 1. If I ask you how many angular nodes are there, how many angular nodes are there? Angular node means L value is 0. If I ask you how many spherical nodes are there, how many spherical nodes are there? N minus L minus 1, the value comes out to be 1. This is something you guys know. This is something you guys know. Now do remember, in case of s orbitals, whenever you need to make psi square versus r graph, or when you need to make psi versus r graph, the graph will be started from the top. The graph starts from the top in case of S. And in case of P, the graph starts from bottom, so that you can remember it. I'm just telling you the tricks to remember, that's all. Okay, now have a look. The first graph which I'm plotting, that is psi square versus r. That is psi square versus r. For which subshell? It's 2s. I'm making it for 2s. The graph is going to start from the top, right? Now in case of 2s, how many total nodes are there? One total node. One node is there. And which node is it? It is the spherical node basically. There is one node, and which one in particular? It's a spherical node. That means in 2s, you will find one spherical region. In 2s, you will find one spherical region where the probability of finding the electron will be 0, where psi square value will be 0. In case of 2s, there is one node, and that particular node is spherical node. That means there will be one spherical region in 2s where the probability of finding the electron will be 0. The graph starts from, since it's 2s, the graph starts from top. Now it's going to touch this r axis here at one position. At this particular point, psi square value. At this particular point, psi square value is 0. So it represents a node. So there is only one node. This is the node. And which node is it in particular? It is a spherical node. Got it? Now, dear students, one more thing. If I want to make the graph between psi versus r, till now I was making the graph between psi square versus r. Now it's between psi versus r for 2s, for psi versus r. Do remember, psi square value, it's always positive, but psi can be positive as well as negative. Since it's 2s, the graph starts from top. It's going to touch the r axis at one position only, and that position is going to represent a node. So one node here, that's all. This is the node for 2s. Let me give you one more example so that it becomes clear. For example, I've got 3s. Let's not 3s, 3s only. I'm talking about 3s. You tell me in the chats, what is the value of n? N value is 3. What is the value of L? L value for S is 0. How many total nodes are there? N minus 1, 3 minus 1, that means 2. How many angular nodes are there? Angular nodes means the value of L. L value is 0, so no angular node. How many spherical or radial nodes are there? Tell me. N minus L minus 1. 3 minus 1, that comes out to be 2. Correct? In total, there are 2 nodes. Right? Perfect. And all these 2 nodes, these are spherical nodes. So in case of 3s, you will find 2 spherical regions. Where the probability of finding the electron will be 0. Yeah? Perfect. Somebody has starting spamming the chats with PW Alak Pandey sir. He's a great teacher, he's a wonderful teacher, but don't spam it here, yaar. Let me concentrate, let others concentrate as well. All the teachers are wonderful, okay? You are getting benefited from everywhere, so there is no need to spam here or somewhere else. Just be a little mannered, okay? Have a look now. Dear students, look at this particular one now. In case of 3s, we got to know there are 2 total nodes, correct? There are 2 total nodes basically. And all these total nodes, these are spherical. Right? Perfect. Now in case of 3s, I want to make a graph between psi square versus r. Now you tell me, is the graph going to start from the top? It is 3s. Right? Since it is 3s, the graph is going to start from the top. So let me make the graph between psi square and r. The graph is going to start from the top. How many total nodes are there? 2 nodes. So the graph is going to touch the r axis at the 2 places. This is 1, this is 2, and like this. These are the 2 nodes, psi square versus r. Now, if I ask you to make a graph between psi versus r, the graph again starts from the top. Now, psi can have positive as well as negative values, right? Yes. So it's going to be from here. 2 nodes, right? So this is the first node. This is the second node. Like this. Perfect. So this is psi square versus r. This is psi versus r. Similarly, now let's be quick. 4s. How many total nodes? Total nodes in case of 4s. That is 3. 3 total nodes. Plot a graph between psi square versus r. Plot a graph between psi square versus r. So the graph has to touch at 3 points. The graph has to touch the r axis at 3 points. Since it's S, so the graph has to start from the top, right? So 1 node, second node, third node, like this. 1, 2, 3. 3 nodes in total, right? Perfect. Now make a graph between psi and r. Now make a graph between psi and r. Psi can have positive as well as negative values, right? At 3 points it's going to touch. 1, 2, 3. 1, 2, 3. Perfectly done and dusted. So this is how you make psi versus r and psi square versus r graphs for the s orbitals. Now what about p? What about p? Before talking about p, let me know in the chats if everything is clear till here. Let me know quickly in the chats if every single thing is clear till here. Everyone. Then only I'll be discussing p with you. All the p graphs, either psi square versus r or psi versus r, they start from the bottom. That's something which I've told you. Now, in case of 2p, the value of n is 2. The value of L for p subshell is 1. Correct? So, total number of nodes will be 2 minus 1. That means 1. The total number of nodes will be 1. Right? Now, if I ask you how many angular nodes will be there, angular nodes means the value of L, that's 1. So, there is 1 angular node. So, how many spherical nodes will be there? There will be 0 spherical nodes. Okay. Now, let's plot the graphs. Plot the graphs. Plot the graphs. Plot the graphs. First of all, it's 2p. The graph is going to start from the bottom. The graph is going to start from the bottom. Correct? Now, the first graph which we are going to plot, that's going to be between psi square versus r. Psi square versus r. How many total nodes are there? 1 node. The graph is going to start from the bottom. From here, it's going to start. 1 node. So, this is the node only, right? Psi square is 0 here. It's a node only. The graph is like this. It's for 2p. Correct? If I want you guys to plot a graph between psi and r, for the same 2p, since it's already above, there is no part which is below, so the graph is like this only. Psi versus r for 2p. Correct? Perfect. One more example. With that, we'll be moving ahead. Let's say you've got 3p. In case of 3p, we know the total number of nodes when you calculate, total number of nodes will be 2. Angular nodes, if you calculate, that will be 1. Spherical nodes, if you calculate, that will be 1. Now plot the graphs. The first graph has to be between psi square versus r. Since it's for p, the graph is going to start from the bottom. So from here, it is a node already. Which node it is? It is the angular node here. It is the angular node here. How many nodes in total? 2. Out of 2, 1 is here. So it goes up. 1 more. Like this. So in total 2 nodes. This one, it is a radial node. It is the radial node. Okay? Like the spherical node. Similarly, if you want to make it for, if you want to make a graph between psi versus r, if you want to plot a graph between psi versus r, start from here only. Take it up. 1 node, second node. 2 nodes only, right? We had to represent. So these are the 2 nodes. So it's a graph for 3p. Let me know once in the chats if it is clear now. Everyone in the chats, people. Then only I can move ahead. Yes, you can take random points here because you don't have to remember the exact values. Just random points. Clear to everyone? I want thumbs ups in the chats if it is super duper clear to everyone. Then only I can move on to a few more concepts. Everyone with the thumbs ups, quickly. Quickly, guys, yeah. And I can see not everyone has liked the video yet. That's strange and sad at the same time. Yeah. Perfect. Let's move on now. So whatever concepts were there in your atomic structure, which are the most favorite topics from which question probability is maximum, that I've discussed with you. Now let's discuss few important concepts from the chapter redox reactions. Are you ready for redox now? Are you ready for redox? Quickly? Quickly, everyone. No break. There won't be any break at all. Guys, there'll be no break at all. Okay, do not ask for the breaks. We have to finish it off. I'm not going to leave you. Just be there. This will be done in just half an hour. I'll try to finish it off, okay? Perfect. Just a second. Yeah, now it's fine. All right. Let's talk about something called as oxidation state first. Okay. What is oxidation state all about? How do we define the oxidation state? Oxidation state, it's basically the charge present on an atom, of an element in a given compound. The charge present on an atom of an element in a given compound is what we call as oxidation state. Now you must be thinking, what is that? What is meant by that? Let me take one simple example. For example, I'm taking an ionic compound. I'm taking one ionic compound, that's NaCl. This is the ionic compound I'm taking. In case of NaCl, how many elements you have? You have got 2 elements. If I ask you, what is the charge present on sodium? What is the charge present on chlorine? How you are going to tell that? How you are going to talk about that? See, this sodium, it is metallic in nature. This chlorine, it's non-metallic in nature, right? If sodium is metallic, it has got strong tendency to lose electrons. If chlorine is non-metallic, it has got strong tendency to gain electrons, right? Now sodium, it belongs to group 1. It has got only 1 electron in the outermost shell. Sodium, it has got only 1 electron in the outermost shell. So this sodium is going to lose that outermost electron. It will get converted into Na positive. Now this 1 electron given by sodium, it will be gained by chlorine, and chlorine gets converted into Cl negative. Now you have Na positive. Now you have Cl negative as well. You have Na positive as well as Cl negative. You have got cation as well as anion. Can I say there will be electrostatic force of attraction between cation and anion? This electrostatic force of attraction between the cation and anion is something which you call as ionic bond. This is something which you call as ionic bond. And that compound in which ionic bond exists, that compound is something which you call as ionic compound. Now, dear students, if I ask you, what is the charge present on this sodium over here? You will say this sodium has got charge of +1 units. This chlorine has got the charge of -1 unit. The charge present on the atom of an element is something which we call as oxidation state. So if I ask you now, what is the oxidation state of sodium here? It's +1. What is the oxidation state of chlorine here? It's -1, right? Simple. Correct? So this was about what? This was about the ionic compound. This was about the ionic compound, correct? Now what about covalent compounds? What about covalent compounds? If you talk about a covalent compound, for example, you have got AB. We have got a covalent compound AB, right? There is a single bond which is existing between A and B. Let me assume B is more electronegative than that of A. Let me assume B is more electronegative than that of A. If B is more electronegative, that means B has more tendency to drag this electron pair towards itself, due to which it gets delta negative and it gets delta positive. Now, if I ask you what is the oxidation state of A over here, you'll say +1. If I ask you what is the oxidation state of B over here, you'll say -1. As simple as that, right? Similarly, dear students, let's assume there's a double bond between A and B. Let's assume there's a double bond between A and B. Let's again assume B is more electronegative. So both the bonded pair of electron will be dragged towards B, due to which it gets -2. This gets +2. So oxidation state of A over here is +2. Oxidation state of B over here is -2. And let's assume there is a triple bond between A and B. There is a triple bond between A and B. And I'm assuming B is more electronegative than A. So all the three bonded pair of electrons will shift towards B, due to which this B gets -3 and A gets +3. Correct? So oxidation state of A over here is +3. Oxidation state of B over here is -3. As simple as that. Now, for example, let's say you are taking the case of HF. This is HF, right? You know, in the periodic table, fluorine is more electronegative, followed by oxygen, followed by nitrogen. You know it. Now, if fluorine is more electronegative, the electron pair is going to drag towards fluorine, due to which it gets delta -1, it gets +1. The oxidation state of hydrogen here is +1, here it's -1. This was just the basics of oxidation state, right? Now, what we have to remember basically? We have to remember the rules from which the question comes. Rules to calculate oxidation state. Let me give you quickly the rules to calculate the oxidation state. First rule to calculate oxidation state, what is that? Whenever you see an element present in its standard state, whenever you see an element present in its standard state, remember the oxidation state of the element is taken to be 0. What is meant by that? What is meant by that? What is standard state of an element? Standard state, it is the most stable state of an element. It is that state of an element in which the element exists in the nature. For example, oxygen in nature exists in the form of O2 gas. So this O2 gas, it is a standard state of oxygen. Nitrogen exists in the form of N2 gas. This N2 gas is the standard state of nitrogen. Correct? Yes. Similarly, iron. Iron exists in the form of Fe solid. Standard state of iron. Correct? Yes. And whenever element is present in its standard state, its oxidation state is taken to be 0. The oxidation state of oxygen here is 0. Here it's 0. Here it's 0. Number 1, the first rule. The second rule. Whenever you talk about the group first elements and group second elements, group first means lithium, sodium, potassium, rubidium and cesium. Group first elements. They always show the oxidation state of +1. Your group second elements, that is beryllium, magnesium, calcium, strontium, barium. These are group second elements. They always show the oxidation state of +2. The first rule, whenever you see an element present in its standard state, its oxidation state is 0. Number 2, group first elements, they'll always show +1 oxidation state. Group second elements, they'll always show the oxidation state of +2. Why is that? Because group first elements, they have got only one electron present in the outermost shell. They can easily leave that one electron, lose that one electron and get +1 charge. Group second elements, they have got 2 electrons present in the outermost shell. They can easily leave those 2 electrons, lose those 2 electrons and get the +2 charge. As simple as that. This was the second rule. Similarly, talking about the third rule. This particular rule is for hydrogen now. It's for hydrogen. Whenever you see hydrogen attached to more electronegative element than itself, whenever you see hydrogen attached to more electronegative element than itself, do remember the oxidation state of hydrogen will be taken as +1. The oxidation state of hydrogen will be taken as +1. It will be taken as +1. +1. Whenever you see hydrogen attached with more electronegative element than itself, its oxidation state will be taken as +1. For example, you have got HCl, you have got HF, you have got H2O. Everywhere hydrogen is attached to more electronegative element than itself. So everywhere you will be taking the oxidation state of hydrogen as +1, right? But whenever you see hydrogen attached to less electronegative element than itself, whenever you see hydrogen attached to less electronegative element than itself, the oxidation state of hydrogen will be taken as -1, right? And what are the less electronegative elements than hydrogen? These are going to be your group first and group second elements. These are considered to be less electronegative than that of hydrogen. Now, if I ask you, what about lithium hydride, LiH? LiH. In case of LiH, hydrogen is attached to group first element. Hydrogen is attached to that element which is less electronegative than hydrogen. So here oxidation state of hydrogen is -1. Simple. If I talk about MgH2, hydrogen is attached to less electronegative element than itself. Its oxidation state is -1. Correct? As simple as that. Perfect. So do remember these two rules related to hydrogen. Similarly, there are few rules related to oxygen as well. Whenever you see oxygen attached to less electronegative element than itself, the oxidation state of oxygen generally is taken as -2. Whenever you see oxygen attached to less electronegative element than itself, the oxidation state of oxygen is generally taken as -2. Right? There is something called as peroxides. What are peroxides? What are peroxides? My dear students, whenever you see oxygen present in the form of O2 dinegative, whenever you see oxygen present in the form of O2 dinegative, do remember that compound is what you call as peroxide. And in case of peroxides, the oxidation state generally is -1. The oxidation state of oxygen is generally -1. For example, let me give you the example of peroxide. Let's say you have got H2O2. This is what you call as hydrogen peroxide, right? Hydrogen peroxide. Look at the structure of hydrogen peroxide. Every one of you must be knowing. Open book like structure. This is the structure, right? If I ask you to talk about this particular bond, check this bond, which is between oxygen and hydrogen. Now, if I ask you which one is more electronegative, oxygen or hydrogen? Oxygen is more electronegative than hydrogen, so bond pair will be shifted towards oxygen. So this oxygen carries -1, it carries +1. Similarly, talk about this particular bond. This oxygen carries -1, this carries +1. Now talk about this particular bond. On both the sides, you have got oxygen. The tendency with which this oxygen is going to attract the bonded pair of electron towards itself, with the same tendency, the other oxygen is going to attract the same bonded pair towards itself, due to which the bonded pair is going to remain at the center, right? So what is the charge present on this oxygen now? -1. What is the charge present on this oxygen? -1. So oxidation state of oxygen over here is -1. Whenever you see oxygen single bond oxygen, this type of linkage, oxygen single bond oxygen linkage, this linkage is what you call as peroxide linkage. This linkage is what you call as peroxide linkage. Perfect. Wherever you see oxygen single bond oxygen, it's what you call as peroxide linkage. Perfect. Clear? Similarly, there are something called as superoxides. There are something called as superoxides. Whenever you see oxygen present in the form of O2 negative, whenever you see oxygen present in the form of O2 negative, that means it's a superoxide. In case of superoxides, the oxidation state of oxygen is taken to be -1/2. It's simple. See, the charge present on two oxygen atoms is -1. So on one oxygen atom, the charge is going to be -1/2. The charge present on one oxygen atom is -1/2. and the charge present on one atom of an element is what you call as oxidation state. Simple. Correct? Perfect. At the same time, there is something called as oxyfluorides. Oxyfluorides. These are the compounds wherein oxygen shows positive oxidation states. These are the compounds wherein oxygen shows positive oxidation states. For example, you talk about OF2. You talk about O2F2. These are what you call as oxyfluorides. These are what you call as oxyfluorides. And in case of oxyfluorides, oxygen shows the positive oxidation states. For example, look at the structure of OF2. The structure of OF2 is like this, right? Now people, talk about this particular bond between oxygen and fluorine. Which one is more electronegative? Fluorine is more electronegative. So this bond pair is shifted towards fluorine. So this is -1. This carries +1. Due to this particular bond, -1. This carries +1. What is the total charge present on oxygen? It's +2. So +2 is the oxidation state of oxygen in case of OF2. Simple. Similarly, in case of O2F2, the oxidation state of oxygen will be +1. Correct? Now, my dear students, now comes a point. Do remember the sum of oxidation states of all the elements. The sum of oxidation states of all the elements present in a compound is equal to the net charge present on the compound. What is meant by it? Now understand, this is important now, okay? This is important. For example, I have got MnO4 negative. I want you to calculate the oxidation state of manganese here. How you are going to do it? Let's say I have got Cr2O7 di negative. I want you to calculate the oxidation state of chromium here, right? Let's say I have got Ki3. I want you guys to calculate the oxidation state of iodine here. Let's say I have got Fe3O4. I want you guys to calculate the oxidation state of iron over here, right? Similarly, let's say I have got NH4NO2. I want you guys to calculate oxidation state of these two nitrogen atoms here. Let's say we have got, for example, CrO5, or leave CrO5 aside. Let's talk about these simple examples for now. See guys, understand. I need to calculate the oxidation state of manganese. Let's assume the oxidation state of manganese is X plus. Oxygen normally shows -2 oxygen state. There are 4 oxygen atoms. The net charge present over here is -1. So X value after solving comes out to be +7. So +7 is basically the oxidation state of manganese over here. Simple, basic. Calculate the oxidation state of chromium here. Let's assume the oxidation state of chromium is X, but there are 2 chromium atoms. Plus, oxygen will show -2 oxygen state, 7 oxygen atoms, net charge -2. So X value after solving comes out to be +6. So +6 is the oxidation state of this chromium over here. Simple, right? Similarly, if you talk about this Ki3, potassium, it belongs to group 1. Group 1 shows +1 oxidation state. Let's assume the oxidation state of iodine is X. There are 3 iodine atoms. It's 3X. The net charge is 0. X value after solving comes out to be -1/3. So the oxidation state of iodine here is -1/3. Fe3O4. Fe3O4. When you solve it, let's assume the oxidation state of iron is X, so it's going to be 3X. Oxygen will show -2 oxygen state. There are 4 oxygen atoms. Net charge is 0. X value after solving comes out to be +8/3. So iron will have +8/3 oxidation state here. Fractional oxidation state. Yes, fractional oxidation state is going to show. Perfect. Similarly, you have got NH4NO2. NH4NO2. Let me tell you, this NH4NO2, it exists in the form of NH4 positive and NO2 negative. It exists in the form of NH4 positive and NO2 negative. Now calculate the oxidation state of this nitrogen and this nitrogen. Let's talk about this particular nitrogen. Let's call it as X plus. Hydrogen shows plus 1 oxygen state. There are 4 hydrogen atoms. Net charge is plus 1. Solve the value of X. You'll be getting it as -3. So -3 is the oxidation state of this nitrogen. Similarly, talk about this particular nitrogen. Let's assume its oxidation state is X. Oxygen is going to show -2 oxygen state. 2 oxygen atoms. Net charge -1. X value will come out to be +3. So oxidation state of this nitrogen is +3. Let me know in the chats if you can solve these type of basic equations. Yes? These sort of basic equations you can easily solve. I'm damn sure about that, right? Now, whatever I'm going to teach you now, that's going to be something different, which I'm not sure whether you have studied or not. Okay? See guys, I'm writing one simple statement over here. The statement is like this. The maximum oxidation state of an element, the maximum oxidation state of an element can never be greater than +7, except osmium in osmium tetroxide, where the oxidation state of oxygen is, where the oxidation state of osmium is +8. This is one important rule which I would want you guys to remember from now onwards. The maximum oxidation state of an element, it can never be greater than +7. Exception is there. What is that? Osmium, in case of OSO4, it shows +8 oxidation state. Well, this was once asked in your AIMS examination. What is the oxidation state of osmium in OSO4? It is +8. Now, why this rule is important? Why this particular rule is important? Now you'll get to know why this rule is important. I'm writing CrO5. Let me know in the chats quickly, what should be the oxidation state of chromium in CrO5? Quickly, everyone. What do you think? What should be the oxidation state of chromium in case of CrO5? Quickly, I'm looking at your chats only. Everyone, quickly, what should be the oxidation state of chromium in case of CrO5? Quickly, guys. I want everyone to write the answer. I can see few people are saying +10, few people are saying +6. So normally, the way I told you to calculate the oxidation state, if you are going to do that way you'll get the wrong answer. Why? See, let's assume the oxidation state of chromium is X. Oxidation state of oxygen is -2. There are 5 oxygen atoms. Net charge is 0. So X value after solving comes out to be +10. So from this, the oxidation state of chromium has to be +10. But read the statement. Oxidation state of an element can never be greater than +7. But here is coming +10. That means you are doing something wrong. Right? You are doing something wrong. Now, dear students, whenever, by means of this particular result, by means of this particular formula, whenever the oxidation state of an element comes out to be greater than +7, at that point of time, you have to draw the structure of that particular compound. Whenever, by using this particular result, the oxidation state of an element comes out to be greater than +7, at that point of time, you have to draw the structure of that particular compound. So basically, you need to know the structure of CrO5, then only you can know its oxidation state exactly. Now, there are few very, very, very important structures which I would want you guys to remember. Very important structures. The first structure, that is CrO5. Let me tell you, the CrO5, it has got a butterfly structure. It has got a butterfly structure. The CrO5, it is deep blue in color. It's deep blue in color. Now how it looks like. This is chromium, double bond O, oxygen, oxygen, there is a single bond. Oxygen, oxygen, there is a single bond. This is the structure of your CrO5. Now dear students, this is chromium double bond oxygen here. Look at this particular bond. Chromium double bond oxygen. Now you tell me, this oxygen is more electronegative than that of chromium. So both the bonded pair of electrons will shift towards oxygen, due to which oxygen gets -2 and chromium due to this double bond gets +2. Due to this single bond, oxygen will get -1, chromium +1. Due to this single bond, oxygen -1, chromium +1, -1 at the same time +1, -1 at the same time +1. If I ask you, what is the total charge present on chromium here? You will say it's +6. So +6 is the oxidation state of chromium in CrO5. Number one. Number two, if I ask you how many peroxide linkages are there? Oxygen, single bond oxygen, this is a peroxide linkage. This is one more peroxide linkage. So how many peroxide linkages are there? Number of peroxide linkages over here are 2. And do remember, if the question comes, how many oxygen atoms are there with the oxidation state of -1? It's always equal 2 times the number of peroxide linkages. So 2 2s are 4. There'll be 4 atoms, 4 oxygen atoms, which will have the oxidation state of -1. This oxygen, -1, -1, -1, -1. Correct? So this was the first structure, CrO5, which you are going to remember from now onwards. The second structure, that's CrO6. CrO6. What about its structure? It's Cr, oxygen, oxygen, bond, oxygen, oxygen, single bond, oxygen, oxygen, single bond. This is CrO6 structure. Now dear students, look at this. Look at this. This is chromium single bond oxygen. Oxygen is more electronegative. So this is -1, this is +1. Single bond, -1, +1, -1, +1, -1, +1, -1, +1, -1, +1. What is the total charge present on this chromium here? 1, 2, 3, 4, 5, 6. It's again +6. If I ask you how many peroxide linkages are there, look at this. Oxygen, single bond oxygen, 1 peroxide, second peroxide, third peroxide. So how many peroxide linkages are there? Number of peroxide linkages over here are 3. So how many oxygen atoms will be there with the oxidation state of -1? There'll be 6 oxygen atoms with the oxidation state of -1. Right? So this was your CrO6. Talking about the third compound. That is H2SO5. You call it as the Carose acid. Now what this H2SO5 structure looks like? It's simple. S double bond O, oxygen attached with hydrogen. Here also oxygen attached with hydrogen. This is your H2SO5, Carose acid. Now people, look at the structure and calculate the oxidation state. This is S double bond O, oxygen being more electronegative. So it will drag both the electron pairs towards itself. So sulfur will get +2 due to this double bond. Due to this double bond, sulfur again +2. Due to this single bond, sulfur +1. Due to this single bond, sulfur +1. What is the total charge present on sulfur? +2, +4, +5, +6. So it's +6. Oh, sorry, this is oxygen and this is hydrogen. Right? It's H2SO5. Now if I ask you, how many peroxide linkages are there? This is oxygen, single bond oxygen. It's a peroxide linkage. So number of peroxide linkages over here is 1. Right? How many oxygen atoms are there with the oxidation state of -1? It's 2. 2 oxygen atoms are there. This is third important structure. Right? H2SO5, Carose acid. Fourth one is your H2S2O7. You call it as oleum. What is the structure of oleum? How do you draw it? This is S, this is oxygen, this is sulfur. Double bond O, double bond O, double bond oxygen, double bond oxygen. This oxygen attached with hydrogen. This is oxygen attached with hydrogen. Correct? Now I can say the oxidation state of this particular sulfur, when you check it, it's +5. This particular sulfur, it's +5. Right? Do remember this as well. This is the structure of your oleum. Similarly, dear students, look at the fifth structure. That is your H2S2O8. It is called as the Marshall's acid. What about the structure of Marshall's acid? S, O, O, this is S. Double bond O, double bond O. Oxygen attached with hydrogen. Oxygen attached with hydrogen. Now calculate the oxidation state of both the sulfur atoms. This sulfur here is at +5 oxygen state. Even this sulfur is at +5 oxidation state. You can check it out too. This is sulfur double bond or oxygen, right? So +2 for sulfur due to this double bond. +2 for sulfur due to this double bond. My +1 for sulfur due to this single bond. +1 for sulfur due to this single bond, right? So it won't be +5, it will be +6. This is +6. I did a mistake in the last one, I think, right? Did I write +2, +4, +5, this is +6, guys, sorry. This is +6, okay? Just change it. It's +6, it's not +5. Right? So this sulfur is in +6 oxygen state, even this sulfur is in +6 oxidation state. H2, S2O8. Now talking about the sixth structure, that is your K3CrO8. How it looks like. Cr, oxygen, oxygen, single bond, oxygen, 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 single bond, single bond, single bond. This is potassium, one more potassium, one more potassium. When you solve it, 1, 2, 3, 4, 5. So oxidation state of chromium here will be +5. Correct? It will be +5. Right? Perfect. It is your K3CrO8. Similarly, the seventh one. Na2S4O6. Its structure looks like this. This is the structure of your Na2S4O6. Okay. This sulfur here, it is in +5 oxidation state. This is in 0 oxygen state. This is in 0 oxygen state. This is in +5 oxidation state. Why this sulfur is in +5 oxygen state? You can check it out too, right? You know it now. You know it now. You know it now. This is a double bond here. Sulfur and oxygen. Oxygen is more electronegative. So both the bonded pair will move towards oxygen. So oxygen will get a -2. Sulfur will get +2. Similarly, due to this double bond, sulfur +2. Due to this single bond, sulfur +1. Due to this single bond, nothing is going to happen. So this particular sulfur has got the total charge of +5, which I mentioned here. Rest, you can check on your own. Right? Someone is asking about the PDF. t.me/WASSIN/SIRCHEM. This is my channel. Anyways, you are going to get it in the official Telegram channel of this Unacademy NEET English channel as well, right? You'll get the link afterwards. On this particular as well, you'll be getting. So this was your Na2S4O6. Moving ahead to the eighth one. I am writing H3PO2, H3PO3, H3PO4, and H3PO5. What about their structures and oxidation states? This is P double bond O, oxygen attached with hydrogen. This is hydrogen, this is hydrogen. Structure of your H3PO2. Structure of your H3PO3. This is double bond O, oxygen, oxygen, attached with hydrogen, attached with hydrogen. This is one hydrogen directly attached with phosphorus. Similarly, your H3PO4, P double bond O, oxygen, 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 hydrogen, hydrogen, one more hydrogen, H3PO4. Similarly, talking about H3PO5. This is your H3PO5. Since you got the structures, now you can easily talk about the oxidation states of phosphorus everywhere. Have a look now. If you talk about this particular phosphorus, P double bond O, oxygen is more electronegative. Both the electron pairs will shift towards oxygen. So this will get -2, this will get +2. Due to this single bond, -1, +1. Due to this single bond, phosphorus is more electronegative. It will drag the electron pairs towards itself. So -1, hydrogen +1, -1, +1. Now calculate the total charge present on this phosphorus. +2, +3, and -2. So it's +1. Similarly, when you solve this, check it out. +2 due to the double bond, +1 due to the single bond, +1 due to one more single bond. So +2, +3, +4, +4 -1. It is +3. Here, it's going to be +5. Here, it's going to be +5 as well. I hope this is clear. I hope this is clear, right? Perfect. So do remember this particular scenario as well. Now there are a few more structures, people. One is your CaOCl2. You call it as the bleaching powder. You call it as the bleaching powder. And its structure is again important. This is Ca, this is OCl, and this is Cl directly, right? Oxidation state of this particular chlorine is -1, okay? Oxidation state of this particular chlorine is +1. If one chlorine is having +1, one more chlorine is having -1, that means the average oxidation state of chlorine, that means the average oxidation state of what? Of chlorine is going to be 0 in case of your bleaching powder, CaOCl2. Similarly, you have got BaSCN whole twice. BaSCN whole twice. You have to remember its structure as well. You have to remember all these structures, okay? BaSCN whole twice. This is Ba, this is S, this is C triple bond N, this is S, this is C, this is triple bond N, right? Now people, understand. This is barium and sulfur. Sulfur is more electronegative. So due to this bond, sulfur will get -1, it will get +1. Due to this particular bond, sulfur -1, this will get +1. Due to this particular bond, sulfur is more electronegative, -1 again, +1. Due to this particular bond, again sulfur -1, carbon +1. Due to this triple bond, nitrogen -3, carbon +3. Due to this triple bond, nitrogen -3, carbon +3. Now what is the total charge present on this nitrogen? It's -3. Total charge present on the carbon, it's +4. Total charge present on sulfur, it's -2. Total charge present on this barium, it's +2, right? That means you got the oxidation states of all the elements over here. Correct? Yes? Is it clear till here? Let me know once in the chats, everyone. Quickly let me know in the chats if it is super clear. These were very, very important structures which I would want you guys to remember from now onwards. Okay? Let me know quickly in the chats with the thumbs ups, people, if everything seems clear till here. Everyone, the chat box is running very slow. Why is that? The chat box is again running very slow. I don't want this to happen. Quickly let me know in the chats if this is clear, or else I'll stop the session here. Which is actually what you want, huh? That's it. All clear? So this was about the oxidation state, the structures which are very, very important, okay? Perfect, perfect, perfect. All right, guys. Now let's move on to one more important concept, which is what you call as equivalent mass. How do you calculate the equivalent mass of the substance? That's important again. This is one more question which is asked. How do you calculate the equivalent mass of a particular substance? How do you do it? There's a simple formula which you need to remember for now. I'm not going into the details. Simple formula which you need to remember. Equivalent mass of the substance is always equal to the molar mass of the substance divided by the n factor of the substance, which you also call as the valency factor. See, molar mass of any substance you already know how to calculate. It is just you need to calculate the n factor of the substance, divide the two and get the equivalent mass of the substance. So our priority here is to understand how to calculate the n factor of different substances. If you know how to calculate the n factor of a substance, divide the molar mass of the substance by the same n factor, get the equivalent mass. Now one by one, we are going to discuss the n factors. First one, how do we calculate the n factor of an element? N factor of element is nothing, it is just the valency of an element. whatever will be the valency of an element, that's something which you'll be calling as n factor of the element. For example, you have got nitrogen. Its valency is 3, so its n factor is 3. Oxygen, its valency is 2, so its n factor is 2. If you know their n factors, you can easily calculate their equivalent masses. So I must say, equivalent mass of nitrogen here, it's going to be molar mass of nitrogen, 14 grams, divided by n factor, 3. So this is going to be the equivalent mass of nitrogen. Equivalent mass of oxygen is simply going to be what? Molar mass of oxygen, 16 grams, divided by its n factor, that's 2. The value comes out to be 8 grams. As simple as that. Correct? Yes? So dear students, how do we calculate the n factor of elements? Whatever is the valency of an element, that's something which you'll be calling as n factor of the element. Number 1. Number 2. How do we calculate the n factor for the ions? N factor for ions. It is always equal to the magnitude of charge present of an ion. Whatever is the charge present on an ion, take its magnitude only. That's something which will give you the n factor. For example, you have got Na positive. For example, you have got SO4 dinegative. For example, you have got PO4 trinegative. These are different ions basically, right? If I ask you what is the charge present on this Na positive, it's +1. The charge present on sulfate, -2. Phosphate, it's -3. You just need to take the magnitude. Here it's 1. Here the magnitude is 2. Here the magnitude is 3. So this is basically the n factor of Na positive. This is your n factor of SO4 dinegative. This is the n factor of PO4 trinegative. If you got the n factors of the ions, you can easily calculate their equivalent masses. Equivalent mass of Na positive is equal to molar mass divided by n factor, grams. Equivalent mass of sulfate, molar mass divided by n factor. The value comes out to be 48 grams. Equivalent mass of phosphate, molar mass divided by n factor, right? Divided by n factor in grams. That's all. Clear? Is it clear to everyone? Perfectly done? This was how to calculate the n factor of the ions basically. This was the second point. The third point. This is the last topic which is going on, okay? So just be with this, deal with this, that's all. There is one topic which is left here, that's redox titration. That's something which I'll be teaching you in electrochemistry, not here, okay? The third one, that is n factor of salts. How do we calculate the n factor of salts? N factor of salt is always equal to the LCM of charge on cation, comma the charge on anion. LCM of charge present on cation and anion. For example, you have got NaCl. What is the charge present on cation? It's +1. What is the charge present on anion? It's -1. Take the LCM of 1 and 1. LCM of 1 and 1 comes out to be 1. So this one is basically the n factor of NaCl. Simple, correct? For example, you have got MgCl2. Magnesium, its oxidation state is +2. The charge is +2. Chlorine -1, right? So take the LCM of 2 and 1. The value comes out to be 2. So 2 is something which I call as n factor of MgCl2. And if you got its n factor, you can easily calculate its equivalent mass. Molar mass of this divided by n factor of this. That's how you calculate the n factor of salts. Similarly, the fourth one, that is important. How do we calculate the n factor of acids? N factor for acids. N factor of acids is actually the basicity of the acid. N factor of an acid is basically the basicity of an acid. Now, what is basicity? What is basicity? What is basicity? Basicity is defined as the number of H positives an acid donates. The number of H positives an acid donates. The number of H positives an acid donates. Or the number of the number of OH negatives an acid accepts. Or you can say the number of lone pairs an acid accepts. Let's try to understand it. It's important, okay? This one is important. This one is important. For example, I'm taking some simple cases. HCl, H2SO4, H3PO4, HNO3. These are some very simple acids which I'm taking basically, okay? Now you tell me, if I put this HCl into water, can I say it's going to give 1 H positive? If I'll put this H2SO4 into water, it's going to give 2 H positives. This one is going to give 3 H positives. This one is going to give 1 H positive. The number of H positives an acid gives, that's what you call as basicity of the acid. Right? Yes, the number of H positives an acid gives, that's what you call as basicity of the acid. And whatever is the basicity of the acid, that's what you call as N factor. So N factor of HCl is 1, N factor of H2SO4 is 2, N factor of H3PO4 is 3, this is 1. If you got the N factor of these acids, you can easily calculate their equivalent masses. Molar mass divided by N factor, 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 that's it. Clear? Now dear students, if it is clear to everyone, now you tell me. You are going to tell me in the chats. What about the N factor of H3PO2? What about the N factor of H3PO3? What about the N factor of H3PO4? And what about the N factor of H3PO5? Tell me quickly in the chats. I want answers from everyone. I want answers for everyone. And I can see everyone has not liked the session yet. You have to like the session also. You have to subscribe to the channel as well if you want to remain updated about all the sessions. Quickly, what should be the N factor of all these acids? Quickly, quickly, everyone. Chat box is going very slow. What about the N factor of these acids? Quickly. That is the mistake which you guys do. That is the mistake which I was expecting from everyone. It's okay, I'll correct it. All right, let's have a look now. See, before talking about the N factors of these acids, I would want you guys to remember one statement. Do remember an acid donates only that H positive. An acid donates only that H positive which is attached to more electronegative element like fluorine, oxygen or nitrogen. Now you must be thinking, since there are only 3 hydrogens, so it is going to donate these 3 H positives, so its N factor has to be 3. This has to be 3, this has to be 3, this has to be, but that's not the case. That's not the case here. Why is that? If you look at the structure of this H3PO2, it looks like this. This is how your H3PO2 looks like. No doubt there are total 3 hydrogens. But out of 3 hydrogens, there is only 1 hydrogen which is attached to more electronegative element like oxygen. And an acid donates only that H positive which is attached to more electronegative element like fluorine, oxygen or nitrogen. So this acid is going to donate only 1 H positive. So its N factor has to be only 1. Right? If you talk about H3PO3, this is how your H3PO3 looks like. There are no doubt there are basically three hydrogens, but there are only two hydrogens which are attached to more electronegative element like oxygen. So it's going to donate only these two hydrogens in the form of H positives. So two H positives are being donated, so its N factor has to be 2. Similarly, H3PO4, this is P double bond O, this is oxygen, 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 hydrogen, hydrogen, hydrogen. 3 hydrogens will be liberated in the form of H positive, so its N factor is 3. Yes, simple. Similarly, H3PO5, again its N factor has to be 3. Okay, perfect. I hope this is clear. I hope this is clear to everyone. Now, if it is clear to everyone, now I'm going to ask you a question. H3BO3, you can represent it like this as well, BOH whole thrice. You call it as the boric acid. Tell me, when you put boric acid into water, what will be its N factor? I want you to let me know the N factor of this boric acid. Basically, I want you to let me know the equivalent mass of boric acid. Because you know, in order to calculate the equivalent mass of a substance, you need its N factor. So that's why I'm asking you to calculate the N factor. Can you do it? Can you do it? See, a lot of people are saying 3. Lot of people are saying 3. But it's not 3. It's not 3. Why it's not 3? Have a look. See guys, if I talk about this boric acid, its structure is like this. B, this is OH. This is OH. Even this is OH. This is your structure of boric acid. H3BO3. This is the structure of your boric acid, right? Perfect. Now, dear students, when you put this boric acid into water, this is water, H2O. Yes. This oxygen, it has got 2 lone pairs. Absolutely, it has got 2 lone pairs. If I ask you about this particular boron, look at the boron. Look at this boron. Is this center electron deficient center or electron rich center? What do you think? See, look at its outermost shell. 2, 4, 6. It has got only 6 electrons in its valence shell. Only 6 electrons, which is less than 8. So, is this boron center the electron deficient center or electron rich center? It is electron deficient center. If it is electron deficient center, that means this particular oxygen, if it is electron deficient center, this particular oxygen, it has got 2 lone pairs. It can donate one of its lone pair towards this boron in the form of coordinate bond. Since this was electron deficient center, this is electron rich center. So oxygen has donated one of its electron pair towards boron in the form of coordinate bond. Oxygen being the donor species. The donor species gets a positive charge. Acceptor species gets a negative charge. That's what has happened, right? Now you tell me, oxygen is getting the positive charge. Positive charge on an electronegative element, it makes it more electronegative. Positive charge on an electronegative element, it makes it more electronegative. Positive charge on an electronegative element makes it highly unstable. So before it was O, now it's O positive, now it's unstable. It wants to maintain stability. It wants to be stable back. So what's going to happen? One of the OH bond is going to break towards oxygen and one hydrogen is going to leave as H positive. And if bond breaks towards oxygen, this positive charge will be nullified. Right? So tell me, when you introduce this boric acid into water, how many hydrogens are liberated in the form of H positive? One H positive got liberated. But that was not the hydrogen of boric acid, that was the hydrogen of water. So if I ask you, how many OH negatives are accepted? I'm just making the complete scenario like this now. It was boric acid like this, H3BO3. Now you're introducing it in water. What happened basically? You got BOH4 negative. With this you got H positive. So can you tell me how many OH negatives are accepted? There is one OH negative which is accepted by this boric acid. And the number of OH negatives accepted by the boric acid, that defines its N factor. So its N factor, it looks like it is 3, but it's not 3, it's 1. Yes? Let me know once in the chats quickly with the thumbs ups if it is clear. Everyone? Everyone? One more thing. N factor of an acid changes on changing the type of the reaction. N factor of the acid changes on changing the type of the reaction. What is meant by that? Look at this particular scenario as well. I've got the acid as H2SO4. Understand this carefully. H2SO4 plus NaOH plus NaOH. It gives NaHSO4 plus water. This is one of the reaction which I've written. Okay. Similarly, I'm writing one more reaction. It's H2SO4 plus 2 times NaOH. It's giving you Na2SO4 plus 2 times water. How many reactions have I written? I've written 2 reactions. I've written 2 reactions, right? Can you tell me what are the N factors of H2SO4 in both the reactions? I'll be waiting for your answers. Tell me quickly. What do you think? What should be the N factor of H2SO4 in both the reactions? What do you think about this? What is the N factor of H2SO4 in both the reactions? I'm asking you. See guys, if you look at both the reactions carefully, one thing which I would want you guys to know here, which you guys need to understand, one H positive, when it reacts with one OH negative, it leads to the formation of one water molecule, right? Similarly, two H positives, when they react with two OH negatives, they lead to the formation of two water molecules, correct? Correct? That's something which every one of you must be knowing. In the first reaction, 1 mole of water is formed. 1 mole of water is formed. 1 mole of water is only formed when this acid would have given 1 mole of H positive. When this NaOH would have given 1 mole of OH negative. These would have reacted and they would have formed 1 mole of water. So how many H positives this acid is donating? It's donating only 1 H positive. The number of H positives which the acid donates, that defines its N factor. So N factor of H2SO4 in the first reaction is 1. Yes. In the second reaction, look at this particular scenario. How many water molecules are being formed here? 2 water molecules are being formed. That means this acid would have given 2 H positives. This base would have given 2 OH negatives. They would have reacted. They would have led to the formation of 2 water molecules. Now you tell me, how many H positives are donated by this H2SO4? 2 H positives are donated, right? The number of H positives an acid donates, that defines its N factor. So it's 2. Clear? So N factor of H2SO4 in the first reaction is 1. In the second reaction, it's 2. Yes. N factor of H2SO4 in the first reaction is 1. In the second reaction, it's 2. So N factor of a particular substance, it's changing on changing the type of the reaction. That means equivalent mass of the substance. It also changes on changing the type of the reaction. When I'm changing the type of the reaction, N factor of the same substance is changing. That means its equivalent mass is changing. If equivalent mass is changing, can I simply say equivalent mass is a variable quantity, unlike molar mass? Yes? Equivalent mass, it's a variable quantity, unlike molar mass. Is that clear? Is that clear? Right? Let me know quickly in the chats if it is super clear to everyone. Perfect, guys. So similarly, one last case with that, we'll take a leave, okay? One last case with that, I'll be taking a leave. That is N factor of base. How do you get the n factor of base? Simple. Number of OH negatives a base donates. Number of OH negatives a base donates, or number of H positives a base accepts. Let's take few cases first of all. Let's say you have got NaOH. A very simple case. If you'll put into water, it's going to give one OH negative. I must say, this NaOH, it's donating one OH negative. The number of OH negatives a base donates, that defines its n factor. So its n factor here is 1. If its n factor is 1, you can easily calculate its equivalent mass. Simple. You can easily calculate its equivalent mass, right? In the similar way, my dear students, if I, for example, write NH3, I'm writing NH3. It does not have any OH negative. So is it going to behave like a base? Yes, it behaves like a base. This nitrogen, you know, this nitrogen. Nitrogen has got 5 valence electrons. Out of 5 valence electrons, this nitrogen is utilizing 3 of its valence electrons to form 3 sigma bonds. So there'll be 2 electrons left on nitrogen as such in the form of lone pair. When you put this NH3 into water, in the water you have got H positives, which is electron deficient. So this nitrogen is going to donate this lone pair towards H positive in the form of coordinate bond. So can I say indirectly, this NH3, it is accepting one H positive. The number of H positives, a base accepts, that defines its n factor. So NH3, it's accepting one H positive, so its n factor is 1. Right? Similarly, dear students, let's say you've got a base like this, NH2, CH2, CH2, NH2. Tell me, when you put it into water, wherein there are millions of H positive and OH negative, tell me what is going to be the n factor of this particular base over here. Now here you have got 2 nitrogen atoms. One carries lone pair, another carries lone pair as well. This will be donated in this direction, this will be donated in this direction. Correct? So indirectly I can say this particular base, when you put it into water, since in water you have got H positives which are electron deficient, so these lone pair can be donated to H positives in the form of coordinate bonds. So indirectly I can say this base, it's accepting to H positives, and number of H positives accepted by base, that defines its n factor. So I must say its n factor here in this particular scenario, that's 2. Is that clear? Is that clear to you? Yes? Wonderful. If this is clear, one last example with this will end the session, okay? But you guys are going to let me know the answer of this particular question. Let me see whether everything is clear. By the way, I had given you one question as the homework. I would want the answer of that question in the comment section of the video afterwards, right? Perfect. And at the end, let me tell you a few more things as well. See, let's say you have got ZnOH whole twice plus HCl. It gives, for example, ZnOHCl plus water. Perfect. Second reaction I'm writing, ZnOH whole twice plus 2 times HCl. It gives ZnCl2 plus 2 times water. You need to tell me the n factor of ZnOH whole twice in these 2 reactions. Can you give it a try? Can you give it a try? Over here 1 mole of water is formed. That means from this particular base 1 OH negative would have come, or you can say 1 mole of OH negative would have come. Here you are getting 2 moles of water. That means from this base 2 moles of OH negatives would have come. The number of OH negatives donated, that's something which defines the n factor. So n factor of this zinc hydroxide here is 1. In the second case it's 2. So n factor of zinc hydroxide, it's changing the type of the reaction. That means equivalent mass of zinc hydroxide in both the reactions, it's different. Right? It's different. So again, I can say equivalent mass, it's a variable quantity basically. I hope you like the session. Perfect. One thing which I want you guys to mention in the comments. Number one, that is the homework question, right? Its answer. Number two, you'll write day 2 completed. This is something which I would want you guys to write in the comment section. Day 2 completed in the comment section, my dear students. Okay? Perfect. That's how I'm going to see exactly how many people are motivated, how many people are super duper excited about the third session, which we are going to have tomorrow at 8 p.m. And tomorrow we are going to complete 2 chapters. One is states of matter, and another is the solid state. 2 important chapters. So 4 questions, short, in very lesser time, in 2 and 2.5 hours. Okay? Guys, not in the chat box, in the comment section, not in the chat box, in the comment section I'm saying after the end of the session. So with this people, I'll be taking a leave. I'll see you guys tomorrow at the same time. Till then, you guys take care. God bless you all. Love you all. And at the same time, if you're not subscribed to the channel yet, I would want you guys to subscribe to this Unacademy NEET English channel, right? Let's make sure this channel becomes number 1 in days of time, right? Perfect. So take care. God bless you all and love you all. See you in the next session. Bye-bye, guys. Redox, with this, the most important concepts of redox is completed, right? There is one concept left, that is redox titration, which I'll be